And there's one page. Two. Thank you, both of you guys. No. Next one. So this is exam one back. I will post solutions. So this is exam one back. Most of the scores were in the 80s and 90s. I didn't calculate exactly the average, but that's really good being in the 80s and 90s for this. Yes?
So I saw that they had an average on Canvas. Did Canvas do that and not you? Because they actually give us a little thing of like, where are you in the average? Of
Okay.
like, are you, do you
Yeah,
suck
that must
or
just
do
be
you?
obvious. It just automatically calculated
Okay.
based on Canvas. When I see my version of all the grades, it doesn't necessarily compute that, but maybe that's what's that kind of relative to that. But you know that if I had to make cut points, you know, based on the the 90s or in the A's and the 80s or in the B's, I don't think everybody is in that range, but in the end we put everything together, kind of the contribution from the homeworks and the exams and the project, it all goes together. But it's by and large, you know, with these scores, you know, students are in a good position. Now that you know you can move up, you do a little bit better on the remaining material. If you're doing well, stay with it. You know, keep doing the homeworks. If you look at the solutions, see if you have that. I'll post after class. Right? See if you have questions on details about things. Sometimes with the solutions, I add a little elaboration or a little, you know, kind of more complete explanation of a bit of it. So good. Homework 5 is posted and would be due next Wednesday. It has to do with some of the things with continuous distributions. Continuous random variables, chapter 4. And what we're going to talk about today is things in the beginning of chapter 5, which has to do with joint distributions of possibly multiple variables. So we're going to start making a transition from, you know, probabilities about one variable to thinking about measuring things in experiments, measuring things in surveys or studies, where we measure a bunch of individuals. So they all give you a value. There's a realization from some random variable, some discrete category or some quantitative measurement, and what's the distribution of those things together. And as we take averages or proportions based on a sample, what type of distributions are we dealing with? Yeah. So we start making the transition from just thinking about probability with one variable to multiple and into inference. And eventually we'll try to summarize that. So we have multiple random variables. We might be doing x1, x2, up to xn, a bunch of different variables. In the special case where we would have two variables, we have what's sometimes called a bivariate random variable, a measurement on two things at once. So maybe there's an x and y, just to make it a little distinct there. If things are x and y can both be discrete, they can both be counting things, right? Or they can be both be continuous, like measures of height and weight. They can be related to each other, they can be independent of each other, or you could have one that's a category discrete one, and a continuous, you can have a mix. If the case is that you have just two discrete random variables, call them x and y. then x takes on certain values and y takes on certain values. Then it's described by a probability function, which gives you the probability that x has a certain value and y has its value. And so for all possible combinations of x and y, you get the probability of some outcome. Now, this is also called a joint distribution. It's bivariate in the sense that there's two random variables. You could have trivariate or higher numbers of variables, but bivariate is two. Often we are interested in the relationship between two variables. So it's called a joint distribution because it's jointly, simultaneously, the probabilities for outcomes on both of them. Right? You can take any joint distribution like this and get a marginal distribution, which is a distribution of one variable at a time. By adding up the probabilities across the other variable. By that we mean, so say we want the probability that x equals a value just for that variable. That might be represented as just a p of x. And I would put a little subscript on there to keep track of which variable you're talking about. But it's related to this joint probability that if you add these probabilities over all the values of y, it will add up the probability. We have the value of x and the different changing values of y, and those all added up together give you the probability of an x. We'll do a concrete case to look at that. But if you add the other way, if you add over all the x's, that's going to give you a marginal distribution of, if you want the probability that y equals one of its values by itself, then we're going to sum over the values of x of these probabilities. X in combination, or y that you're interested in, with the combination of all the other x's. Look at all those probabilities and add them up and it's give you the margin. One way to think about this is by having a table, and the handout has some computations related to a table. So let me give you the table that we up here. Right? So the table is going to have an example where it asks about attitudes of something and personalities. And the x variable, kind of in a marketing study, is going to be asking people about attitudes about small cars. Right? And then record some values here. One is going to be that the person is favorable towards this. Two is they're going to be neutral toward small cars, and maybe the other one is that they're unfavorable. So people are going to be asked the question, how do you think about small cars? Would you like to have a small car? Or if you have a rental car, would you like it to be a small car? Would that be good, neutral, or bad? Right? So they respond one of these three cases. The personality type, they're going to ask people to classify themselves or possibly ask a series of questions of how they behave and things that they do. And they're going to be classified as somebody who's cautious or somebody who's kind of mid-road between cautious and then somebody who's more explorer. So in marketing, or personality, they might make up things and see how you associate with these different labels. And so if you see different behavior and preferences by these different groups, those would be interesting labels and possibly useful to you. So let's say that in a population or in a study that we have a distribution of x and y. Here x, y on this one. X can take on the values 1, 2, and 3, and y can take on the values of 1, 2, and 3. And in the middle, on each of those cells, those 9 cells, there's 3 times 3, 9 possible pairs of outcomes. We're going to put probability. So we're going to put 2.264 as a probability here, 0.194, 0.164, 0.033, 0.027, 0.030, 0.033, 0.114, and 0.141. So those are the probabilities there, right? So all those probabilities, these are called the joint probabilities. So this is the probability, one of these probabilities. This is the one where x is 1, and y, x is 3, and y is 1. So that would translate into 3.3% of the people in this study or this population are unfavorable towards small cars, and they're kind of a cautious person. So it would represent the values for both of the variables simultaneously, right? So these are the joint probabilities of two things at once. And if we add across rows or down columns, that's doing the summation to get a margin. Right? So if we add down this way, the probabilities for the different y outcomes are going to be down here. So if you add down these columns, right, these three things add up to 0.330. The chance that y is 2, which is more of a mid-road person, is 0.335. And this one adding down here is also 0.335. They add up to 1. These three numbers add up to 1. The 9 numbers in the middle all add up to 1. And that side is the marginal distribution, represents the marginal probabilities for y. Right? And you can do the same thing for the x and get the marginal probabilities over there. These add up to kind of a big number, 62% or so. This one's 9%, and this one is 288, so about 30%. So maybe this is a thing where people classify themselves in terms of their opinion about cars, but maybe the personality is based on a series of responses to different questions, and they kind of add up the scores based on those, and they kind of split people up into about 1/3 into each. Right? Maybe something like that has happened, where it's kind of divided up, split them kind of equally by the lowest, the middle, and the highest on some scale, and called them cautious, mid-road, and explorer. And the X, though, is responses to their actual opinions. Right? You can get data in a number of ways. Right, so this is the marginal for X. That margin gives the probabilities for the density of X. So a little X on there. This would be the margin for the Y on that one, right? And so that's what's meant by you have a joint distribution of them together, or we have the two margins. Right, another thing you can do with these is you can figure out conditional probabilities. Probability of the levels of one of the variables, given that you're in one of the other groups. Given that these things seem to be kind of divided up equally, we might be interested in, well, what's the opinions of the cars among those three different types of people? So the next thing, right, is we can have a conditional. Once we have two variables, we can condition on something. We can have conditional probability and a conditional distribution. So we can have, we're going to look at the conditional distribution of x given y. So this is the probability that x has a value given that y equals a certain value. Another way that might be phrased is among those at level y, what's the probabilities of x? So among those with y at that level, these are probabilities of x. So a way to calculate a conditional probability is very much like what we do with conditional probability, right? So this is the probability that x equals its value given that y equals its value. And so that can be the joint probability for x and y in the numerator, right, divided by the probability that we're in that group that had little y as its value. Or in that other notation, that's just the p of xy, the joint distribution over the marginal for this. And you could reverse it, right? You could do y given x if that was of interest, but in this one we're going to look at the opinions of cars based on what the other people say. That's y over here. And so it follows the conditional probability. The thing you're conditioning on stays in the denominator. That's what you know, that's kind of your base. So let's make a little table of conditional probabilities. So for the values of y, say y equals 1 or y equals 2 or y equals 3, we could look at the probability of the x values given that y equals 1, or the probability of the x values given that y equals 2, and the probability of the x values given y equals 3. X can take on values of 1, 2, and 3. So the probability that you have at x equals 1, probability that x equals 1, given that y equals 1, well, there was 20.264. Yes?
Just go back to the slide for a second. Sorry.
The previous one, yeah? Right, so it's going to be a conditional probability. So you take the probability of two things at once over the marginal.
Right. Thank you.
Sure. So for my table, 26.4% had both y1 and x1. Right. And then we figured out that the probability y equals 1 was 0.330. And that actually ends up being 0.8. Dot. If you, right, so 80% of those that had y equal 1 said 1, which was favorable for the small cars. The chance that you get 2, there was now y is 1 and x is 2, so in the chart that's 0, 3, 3. Now the chance that y equals 1 is again 0.330. That denominator is the same. It's still conditional on y equals 1 category. And that's 10%. And the chance that x equals 3, given that y equals 1, this conditional probability, is the same. Was 10% of the people. How does it change when we go to y equals 2? Right, we're interested in, for the different second group of people that's kind of more cautious, or the one that's more explorer-like, what are these probabilities? You follow kind of the same pattern. This one ends up being 58%, 8% here, right, and 34% here. These add up to 1 because their probability is conditional on that category. You have to be in one of those 3x categories in that group. These add up to 1. And now in the third category over here, if you did that calculation, this would be 0.49, 0.09, 0.42, and those should add up to 1, except for rounding. So what is the calculation for this one? So the probability that x equals 1, given that y equals 3, so we're going to get the probability that x is 1, y is 3, over the probability that y equals 3. From that table, y equals 1, x equals 3 is 0.033. The chance that, now is that right? X equals 1, y equals 3, so what do I have? X equals 1. What? 0.164. Over, oh wait, is that the wrong number? So y, x is 1, y is 3.164. Right, keeping track of which one. Thank you. And then the chance that you were in that y equals 3 category is the 0.335. So that's almost half, 49%. So that works out. But you can always check that these things are supposed to add to 1. So how do these distributions compare? Is there a difference between these people based on their attitudes towards small cars, their x valuables, depending on how they're classified in terms of personality? Yeah, there's some differences, right? This group is x is 1 is favorable. This one's much more favorable. This one was less favorable. This group doesn't like the large cars. Maybe a little bit the opposite, right? They're not very likely to be unfavorable, but this group is more likely to be unfavorable. This group is also more kind of polarized, right? This one's more clumped. So you get things out of the conditional probabilities. Right? You can put these things into graphs of various sorts, right? You could make just bar graphs for 1, 2, and 3 for each of these and kind of compare them. One type of graph is given the name of a segmented bar graph, where for the different groups, and so we had y equals 1, y equals 2, y equals 3, the probabilities, the conditional probabilities are going to add up to 1. And you could put a bar in here that represents, the value, the probability when x equals 1, and there's smaller values when x equals 3 and x equals 2 in here. And on a computer, you could shape them and kind of show those relative probabilities. The other groups had, probability that was kind of like this, and they had a small group in the middle. This is x equals 1, 2, and then 3. It looked quite a bit different than that one. And this group over here, the third one, wasn't too much different. And I'm not going to get it maybe exactly right proportionally, because I'm kind of doing it rough. It was a little bit more on 3. These two were actually kind of similar, and this one was most dissimilar. And the graph kind of emphasizes that. So sometimes conditional probabilities of graphs in different ways. Right? You can see a little bit more of what's going on. Okay, any questions about following these through? So for variables that are quantitative, now this is maybe not the best example because it's 1, 2, 3 really kind of arbitrary. Right? The 1, 2, 3 doesn't necessarily have a meaning, but I developed this example to show some things. We can do expected value of random variables. And now we have two random variables. We have x, right, and we have y. So there's more things that we can do by taking expectation. Some of the things that we that be interested in would involve both x and y. Right? So if you had a production function that had a bunch of inputs, and they had costs for each one, then your total cost might involve several variables added together. Right? And so there's an average for that. And it depends on the distribution of all the individuals and how they're related to one another and so on. So it could be a little bit more complex. Right? But in the general case, if you have some function, so this is some function of the x and y values that you're interested in. It could be anything, like there could be a cost plus a multiplier times x plus a multiplier times y. It could be, some number like pi, x, y, something like that. It could be quite complex functions of your x and y variables. But you take these two variables, you do something to take the average. It could be simply an average, x plus y over 2. Those functions of random variables You have a random phenomenon, you measure two different things. You put together the measurements somehow by averaging standard deviation, some cost function equation. Well, those are still random variables. They still have distributions. Right? So we can talk about the probabilities associated with those distributions. And we can talk about expected values of these different summaries, these different, the average or other things. So the expected value, E function, of this function of things that we're interested in for a bivariate discrete random variables follows the general idea of that we're going to take the values that our function, the g of y, x, y, can take on. For the values 1, 2, 3, we plug 1, 2, 3 in there. For x, 1, 2, 3 for y. Compute whatever that is. Right? It will give us a value. And we're going to multiply those by the probabilities. So we get those values. But now we have two variables going on, right? So x can change and y can change. So expectation is a sum over all those pairs. So it's a double expectation. Sum over the values of x and the values of y. And that gives the expected value of that xy function, right, that we would see. Yeah?
Does it matter what order you do the summation in if you do the...
A lot of times it doesn't matter,
Okay.
right? If somehow x and y were restricted to each other, right? So sometimes you have a continuous variable where x is the time you have to wait till the first thing that happens, and then y is the time you have to wait till the second thing happens. So y has to be bigger than x. If it's continuous, that'd be more of a double integral. That we'll look at some continuous examples. But if they're not restricted like that, then there won't. You could do either one. And if one's the maximum and one's the minimum, and there could be some kind of relationship between them. But if there's not, then you can go over all pairs. You could go over all pairs probably anyway, but some of these probabilities would have to be zero because if they're not possible. So a couple of specific examples, right? So say we want just the average of the x variable. We're only interested in one variable. If we have the distribution of x, the marginal distribution of x, we can do just what we've done before. Right? We can add over all the values of x of the value x times its probability. That works perfectly fine if you compute that margin. If we have the joint distribution of two things, right, we can also represent this as a sum over all the x and y values. Each time, we're only interested in x. Our function is just that x value. But you can multiply it times the probabilities of x and y. So you can go over, in that example, you can go over all the 9 cells of the table. Each time just keep the value of x, just kind of discard y for the moment. Right? But then add up all those probabilities as they multiply by x. Right? So in the handout, where the handwritten part kind of shows the two ways of doing that for x. And again, maybe this is not the best example because of the, it's really more of a qualitative variable. The average of 1, 2, and 3 in this case, honestly doesn't have that much meaning. So let me go to my handout, a copy of that. And the computer was going really slow when I tried to start it. So here's the handout for this. Here's the copy part. Now you can all sit on your side. So x took on the values 1, 2, and 3. Right? And these are the three marginal probabilities. So with just one variable, that's the average. So you're going to do this experiment, ask people their opinion. Some people are favorable or unfavorable or just mid-road. You get a bunch of 1, 2s, and 3s. Right? Kind of theoretically, you would expect the average of all these scores to be about 1.66, 1.67. If you get a very large sample, it's probably going to be quite close to that because you're going to get about 62.2% ones, about 9% twos, 2.88% threes. Another way of looking at that with a double summation, right, is that in this, well, when x is 1, y can go over 3 different values, 1, 2, or 3. And these are the 3 probabilities that went into that. So you can take that x value that you're only interested in times those 3 probabilities. When x is 2, y also has 3 values, so you can add those up. or when it's 3, you can add those up. It amounts to the same thing, but it's just kind of your perspective. Are you paying attention to the joint distribution or just the marginal? For just the expectation of x, it's just as well to use the marginal distribution of x and do that. If you follow through the standard deviation calculations for just one variable, it's about 0.89. Right? If you do that for the y variable, again, you could do just the y variables, and it's about 2 as an average. That was pretty balanced between the 1, 2s, and 3s, so there's about 2. The other way of looking at that is a sum over y's. Right? This is a case where it doesn't matter whether you put x or y first. But I'm putting it this way because I'm taking the y value equals 1, and then the probability of y with the other x's. So 1, 1, 2, 1, 3, 1, adding those probabilities here. And then 2 times all the probabilities that involve y being 2, and then 3 times all the probabilities involving y equals 3, and you get that. It's the same number, 2.005, and the standard deviation, if you calculated the variance and took the square root of these numbers, is 0.815. Right? But you can do other functions. Right? One particular function that is interesting for describing variables is called covariance or correlation. The thing that goes into calculating this is the expectation of x times y, the product there. So that's this one. The expectation, if you want y, to write it down in these notes. If you have, I'll put an x here. So I added a little x over here to my notes to emphasize that that's the marginal for x, and this is the marginal for y. But this thing is, a sum over the pairs of the value that y is taking on times the probability, the joint probabilities over here. And if you can change those up, right? Change these orders. Probability of x and y. And if that inner sum is over x, well, y is actually constant in terms of x. Right? You get a y value. X can go 1 through 3, but y is whatever it is. So if you pull y outside of this, you get a sum over x of the probability x and y. Here's this sum is here, and this is the next one. So the value of y. This sum of the joint probabilities over x, kind of adding over that column, was just this probability of y. So it's a little bit more formal than I guess it's really helpful to be, but you can, these two things are the same. This other one that we're doing now is the expectation of the product. And so that's a sum over the x and y's. Now the thing that we put in here is x times y, and then the probabilities. And it's not really clear that you would benefit from simplifying that in any way, or sometimes maybe that you could. But anyway, right. So in this example, this expectation, right? Since there's 9 cases, that's the function. We have to take all combinations of x and y. 1 times 1, 1 times 2, 1 times 3, 2 times 1, 2 times 2, and so on. And they get multiplied by their 9 probabilities. Right. So you get the expectation of this function x times y. And that ends up being 3.55. The place that gets used is in covariance. And covariance describes a pattern between the data. So the covariance between 2 random variables. Yeah, I had a middle school science teacher told me my R's and B's need to be better and more distinct. And so it still comes to my mind. I kind of try to make sure what's a B and what's an R. Right? The definition of covariance in general is the expectation of x minus its mean times y minus its mean, right? Where you take the average of these deviations, the product of these deviations, over all the xy combinations, right? Over all 9 cells in that table. The computational way that's a little bit easier, this is equivalent to x times y minus the two means. If you multiply this out, you get 4 terms and a couple things cancel, and you end up with this shorter part. But this representation of it shows you a little something. Right? Now in this picture, in that covariance, so say here's the mean of x, and here's the mean of y. And our probabilities put probabilities on where the pair xy lands. If there's a lot of probability on this space up here and on this space down here, x and y are kind of going together, right? But if you, and so if x tends to be big when y is big, and y tends to be, or x tends to be small when y tends to be small. So this is the xy plane pictured here. Right? And the values we would see for the combinations tend to be, going up or down together, right? Then covariance, right, which should be bigger than 0. Right? And these things should be positively associated with one another. Right? Because if x is up here, it's bigger than its mean, right? It's bigger than this use of x. And also y is bigger than its mean. But down over here, x is less than its mean and y is less. So positive times positive or negative times negative is, and there'd be a lot of probability to put all those combinations. The other way, if you have, again, this use of x, use of y, at that level, if the points tend to be that way, so when x is big, y is negative, and vice versa, right, then you tend to get covariance that's small, negative. So covariance becomes a kind of one number summary looking at the associations here. For this case, the covariance between, I'll just leave it like that. You have it at the handout. The expectation of x times y was 3.55. The two means were 1.66 and 2.005. And so that number comes out to be about 0.21 as a covariance. Right? So that's, right now, just think about that as a number. It's positive, right, as a number. It does depend on what the x scale and the y scale is in there, right? So if we made these numbers 10, 20, 30 instead of 1, 2, 3, we would get a bigger value of covariance. Because the mean of x would be bigger, the deviations would be bigger, and it would be there. So the way to avoid that scale factor is correlation. Correlation takes that covariance and divides by the standard deviation. Correlation of x and y of two variables is their covariance divided by their two standard deviations. So for this example, it was 0.21, and then the two standard deviations were about 0.8 something. Right, there's about 0.89, 0.82 approximately, and it came out to be about 0.9. Sometimes that's given the Greek letter rho. Correlation, sample correlation statistic that we'll look at is sometimes called R. The Greek letter comparison in Greek letters is rho, right? So this correlation, right? Correlation values are between -1 and 1. Correlation doesn't have any units. If x and y were both in feet, right, you have feet squared in the numerator, but you're dividing by the standard deviation of both, so you're dividing by feet, so that there's no units, it's just an absolute number. 0 means there's no correlation. It suggests that there's no linear association between the two variables between x and y. X could be going up, and there's no telling where y is going to go. Right? If it's 1, if there's a perfect straight line, right? If y equals ax plus b, if it is a linear association, if the a is greater than 0, then this correlation is 1. If, however, if a is sloping down, then the correlation is -1. If it's a perfect relationship, and so there's a 1-to-1 trade-off, you're taking temperatures that are measured in a random system, and you're converting them between Fahrenheit and Celsius. And there's a 1-to-1 transformation. The correlation is 1, it's just perfect. Right? If you're viewing something as cost versus expense, so you're just going from positive to negative, right? You have a certain amount that you expend, and you subtract that from your savings, right? There's a 1-to-1 relationship, that's going to be -1. But for almost everything else we're interested in, x and y sometimes go up together, sometimes go down together, you're going to get something in the middle. Right? This one has 0.29 correlation, so it's a moderate positive association, so small to moderate. Look back at the table, right, we could see that as y or x is going up, the other one tends to be going up as well, but not too strongly. So if you look back at some of these tables we had of these things, so then we look at even the bar chart, right? There's a lot of y equals 1 when x equals 1, but as y gets bigger, right, it kind of goes more to the larger values. The larger values become more likely for y equals 2, y equals 3. The big values were unlikely for y equals 1, and so on. Those conditional probabilities kind of show a little bit of association there. Not terribly strong, but it's there. If you look back at the original table, you get more probability on the diagonal. Right? There's a lot of 1 1s, 2 2s not very often, 3 3s. There's kind of a number of probabilities here. There's not much 1 3. There's a little bit of 1 3. There's not much 3 1. So there's a little bit less off diagonal. Again, this is not a strong relationship per se. There's a little bit of tendency to be kind of 1 1 2 2 3 3, more so than off the diagonal. So the correlation in this is probably more meaningful in completely quantitative variables where you would care about how the numbers would have more meaning. But that's correlation and covariance, so some association between these variables. But any questions about this? Right? That's really the discrete case. Right? So you have things expressed this way. There's joint distributions. They can be made into margins. You can make them conditionals. You can make expectation of different things that involve multiple variables. Right? And the general way to do it is to take whatever function, whatever summary of those statistics together, right? And calculate the probabilities at each of those possible combinations. Now, we'll eventually do a continuous one, but I wanted to just kind of emphasize this, with one more. Right? Another example that emphasizes how some of these calculations go, right, and kind of bridges into this statistics is just a simple case of you roll 2 6-sided dice, and we can assume that these things are fair, meaning that the probability of each outcome is equal, right? And we're going to assume that they're independent. So when you roll the pair, right, there's 36 possible outcomes. So here's the first die, and the second die. 1, 2, 3, 4, 5, 6. first one, 2, 3, 4, 5, one more row. Over here. So with this, there are 36 possible outcomes. Say X is the first one, and Y is the second. That when we take something like, you know, in any type of function like the average, I'm going to have x plus y, y over 2 for these, that the function we have in there is can be thought of as another random variable. Right? So x is a random variable. What are you going to get on your first one? Y is a random variable. What are you going to get on your second one? And then the average there is another random variable. Right? It's what are you going to get for an average when you do 2. So there's probabilities associated with x and y. Based on these simple assumptions, it's going to be 1 out of 36 for any of the pairs, right? Assuming that they're equally likely and independent. 36 different outcomes, all equally likely. There's distributions for the different values of x. So if you add across the second one, all of these end up 1/6. The kind of physical description of the process for just that first one is fair, so it's 1/6 for each one. There's a probability distribution for the second one. It's also 1/6 for each of the possible outcomes in 1 through 6. But there's a probability distribution for this. So let's say this is called S or let's call it, well, I guess I'll just call it S bar for like the sum divided by 2, just to make up a symbol, right? That there is I'll just call it S sum. I don't want to use, if we just do x plus y, then we'll just call it S and call it the sum. It's easier to represent. Right? But there's a probability distribution according to the sum here that comes from how these variables are confined and the fact that we've used this particular function. Right? So in this example, right, that do my square a little bit bigger, 1, 2, 3, 4, 5 lines, and 1, 2, 3, 4, 5 lines, and the numbers 1 through 6, and the numbers 1 through 6. And this sum is the process sum of these two things. Well, the smallest sum is 2, obviously. We're getting 1 and 1. All the values, 7, 8, 9, 10, and 11, 12, all those are over there. Those are the possible values. And then the probability that you get one of these values, right, is you have certain values of x and y, certain values of this, right? And some of them will satisfy that the sum you're asking about is the product there. So the probabilities really are this double summation over different values of x and y such that they equal the sum. So here we're adding over really the set of x and y such that x plus y is the sum that we care about, that we're asking about. So we'll say the sum is, say s equals 5. Right? How many pairs, which pairs end up giving us a sum of 5 out of this? You get a 1 on the first die.
1 and 4.
1 and 4. That's one way it can happen.
4, 1.
4, 1. Yep. I'm going to write it 1, 4, 2, 3, 3, 2, 4, 1. Yep. All of those are possible. So there's these four things. If they each have a probability of 1 out of 36, we're adding up these four numbers, and so the probability that you get a 5 is 4 out of 36. If you put the values of the sums in here, this is 2, this adds up to 3, these adds up to 4, these add up to 5, etc., with the last one being 12, and these are the 11s. So there's a 1 out of 36 if you get the smallest on both. There's 2 ways to get 3, 3 ways to get this, 5 ways to add up to 6. There's actually 6 ways to add up to 7. 1 through 6 on this one can be matched to one number over there, and you can get that. 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, and 1 out of 36. These different probabilities. And so the point of kind of mentioning this is, again, that we have a joint distribution of 2 variables at once. But we're going to do something to our set of measurements. Add them together, average them, and it turns into another probability distribution for a different variable. So with the joint, for the binary, for the discrete ones, we have some outcomes like that. Right? The joint distributions, the margins, we can take functions of them and compute the mean of that function, or the variance of it, or the covariance between variables. Right? But the kind of the way that the variables are together then leads to a probability distribution for that sum. So really, we can start with 2, 3, 4 multiple variables, and we're going to do something with it, like an average or a total thing. We're going to calculate something that is like an S. When it's a summary of random variables, it's called a statistic. Yeah?
Can you just scroll down?
Oh, yeah. Now this joint distribution stuff also applies to continuous variables, so at least we're going to look at this briefly. But any questions on the discrete ones on some of these examples? So we're just going to touch on it to introduce that there are joint distributions. For continuous random variables. Let's say we have x and y. Instead of having a probability at every combination of x and y, we can have a density function based on 2 variables at once. X and y. So what would this be? Right? So you imagine there's exam score 1 and exam score 2. Right? And exam score 1 it might have a density function that is, for the values of x, kind of a density function for its variables around some average here with some standard deviation. And it might describe the scores on an exam 1. Now there's an exam 2. Right? It also has a distribution. It might be, so it's a variable y, it might be close, maybe a little bit different. There, it has a density. But people take the both exams, right? So there's a distribution of these things together. Right? And it's hard to picture that. But if you imagine you had a bunch of scores of something, you might have your x value and your y value if you plotted it. And if there's generally a positive association between these, and you actually had points, you would tend to have kind of a positive association. Right? This, these would be like a sample of values. From kind of the 2 variables together. And if the x distribution, these kind of this, if you project these down to the x, it kind of follows that distribution. These follow the y distribution. Together, if there's a positive association, they're going to go together. So in this one, the correlation and the covariance between x and y are greater than 0. So we can look at one quick example to do these. So let's say that we have variables x and y, and the density for x and y is some constant times x plus y. Here's the density. And x takes on values between 0 and 2, and y takes on values also between 0 and 2. And the density is 0 elsewhere. So to actually picture this thing, right, it's really in 3 dimensions. We can't really draw. So imagine there's an xy plane and something sticking up, right? The thing that's sticking up is the density. And the xy plane kind of goes 0 to 2 and 0 to 2. And so there's positive density on that little square there. And c is going to be some number that's greater than 0. And so this function, this x plus y, comes up here at a certain height. So that's sticking up out of there, and then let me do a different color. Right, so this sticks up here some distance. It sticks up here some distance. It sticks up here some distance. And I don't know if this is going to be useful at all to describe this, but then at 0, 0 is a point up here. There's some point up here at 2 plus 2 is 4 times whatever c is, some constant. The c can actually be 1/8, so if you want to know what it is. And then this kind of goes up to here, and this goes up to here, and this goes up to here. So there's a density. You can't see it too well. This red one would be outside of that. Kind of leaning back in there. So, there's a square down here, and then there's this density kind of sitting up on top of it, a height up above it, right? And so, x and y are kind of going together, right? They're both likely to be big, whatever. But anyway, this joint one, these joint densities, just like all of them, have to be greater than or equal to 0. And the area under that whole thing has to be 1. So the integral is actually a double integral. Right? The prerequisite for this class is calculus 1, so you don't necessarily do double integrals in that, but it's very much like the same process of doing one interval. So the integral over the volume underneath that curve is the double integral and has to equal to 1. So in this example, that had this function, the x and y actually go from 0 to 2, and 0 to 2 for the other one. There's a c here times x plus y, dx dy. And so in this particular case, it doesn't matter which order you do. If there are restrictions, like x has to be bigger than y, then that affects the integrals. We're not going to get into really doing cases like that. But the way this integral works is initially you consider x plus y. C is a constant, so that doesn't change. And you do an integral with respect to x. Right? So the integral of x with respect to x, right, is x squared over 2. And then you integrate this y. Now if you think about y as just a number, right, say it was 5, right, then the integral will be 5 times x. And you get the same thing, you get y times x. And you evaluate that, this definite integral, from x going from 0 to 2. Because the x is on the inside, the first integral is related to x. And so we won't do a lot of things with double integrals in any way, but it's perfect kind of illustrate this kind of on this day and the next time just to, yes?
So when you're doing the integral thing, you don't like for the constant, you don't do c times x?
C could come out. It's just it's the same constant as a number. The number is actually going to be 1/8. So it's not going to change. Anything because it's multiplicative. we're gonna finish this one, put this pull C out. When it's 2, that's 4, so there's 2 plus, and then 2 times y. When x is 0, both of those things go away. And then we're down to a just a single integral, so 2 is t times y, plus y squared over 2, the 2's cancel, and you evaluate that at y equals 0 and 2. So it's c times 4 plus 4, or c times 8. And so because it's the density, that thing's supposed to integrate to 1. Right? So we have to have that c, our value over here is 1/8. So we have this density, sorry, I'm going too fast. But anyway, we have this density. Right? And what we'll pick up on, and that's if you look at how it does it in the book, right? If you integrate out one of these, right, you get a marginal distribution for the other one. You integrate out x, you get a marginal distribution of y. Kind of analogous to adding over the one dimension of the table versus the other one. So we can do this type of things that we did today with expectation for variables, but with continuous ones as well. Again, this is mostly kind of an awareness that this goes on and this happens. We're going to transition, after looking at it just a little bit more, to at least go through an example. Right, then we'll transition to really thinking about statistics in the general sense, less mathematically in that sense, but with more of an application focus. So anyway, these are the exams are back. Please do look at the solutions. Feel free to ask about anything on there. Homework is posted based on the chapter 4, and we'll take up more of this chapter 5 on Mondays. Have a good weekend. Yes.
Question.
Yeah.
But this is number 1 is like just to do like between here. This is trying to find like probably like more than 6.
Okay.
So like this is less than 6. I subtracted it.
Yeah.
I got
This value probably then is too
yeah.
big.
Right.
So, what's the density for this one? 1 over 25y.
For 1 2 first minus 1.
So, 0 to 2. So I think with this one, and it looks like it's at the top, it's less than the 2. You can integrate just that, up to that point, less than 2.
Yeah.
But if you wanted to do, and if you're above 2, looking upwards, you can just integrate that little space in there. But if anything you're asking crosses over that 2 points, because the thing is not just one curve.
Yeah,
One
so
curve
for,
up,
like,
one curve down.
between
You said it's gonna curve the
6.
shit out of it, and I was like,
So I was gonna do like less than 2, and what was like less than, I can know it was like less than 6 and more than, less than 2 and more than 6.
Just don't miss class.
So
That's
if you
my
should take
biggest-
1 minus those
Wow,
two
well,
things.
Ballard.
So you
Yeah,
add those
and one of my
together.
friends, he's like,
Right, so if you want, if it's between 2 and 6, you could subtract off 0 to 2, and then 6 and above. And just leave what's left over
Yeah,
in there.
but like, I was trying for getting more than 6, it should be like 1 minus 6, and this was like 1.
So one thing that's going to happen is the function changes, right?
Okay.
So if it were just one equation going up, right, and then you integrated from 0 to 6, it would work out. But if it kind of goes up and then goes down, you're going to get too much.
Okay, so I shouldn't do 1.
So try to do just 6 and above. It's just the density that it has above
Okay.
6, and see if that works